So looking at these reactions in aqueous solution in a little more detail is that if we have a reaction that takes place between ionic compounds and aqueous solution, the products could remain dissolved, as we sort of have discussed here. This typically happens with ionic substances in water, because water's polar, dissolves ionic things. Or the other thing that could happen is that it could form a compound that's insoluble and precipitate out of the solution. And so we said this is the precipitation reaction. Now, because of the fact that the compounds involved in a precipitation reaction are typically ionically bonded, it's sometimes helpful to write the chemical equation, not like we had before in terms of the compounds. We can instead write them out in terms of the dissolved ions and the precipitate compounds in the solution. And so, for example, if we were writing out a chemical formula that involved NaCl, if this is in solution, if it's an aqueous solution right here, instead of writing it this way, we could choose to instead write it something like this, that we have, it's a sodium Na plus ion in aqueous solution. That should be a Q right there. And we could add that, say, plus a Cl minus ion that's in aqueous solution. Okay? Seems like we're doing a little bit more work, but what we're going to find is this is actually helpful in terms of simplifying certain types of precipitation reactions. So to do this, we're going to write out what's called a total ionic equation. And so that's what a chemical equation that's written with the dissolved substances as ions and, of course, the insoluble precipitates. And so let's say that we have this particular equation right here. So AgNO3, silver nitrate, which is an aqueous solution, plus NaCl in aqueous solution, yields AgCl, which is silver chloride, which is, notice that it has the phase notation as S, which indicates it's a solid, which would be that it's a precipitate. It's not dissolved anymore because it's insoluble. And then NaNO3, sodium nitrate in aqueous solution. So looking at these, we have 1, 2, 3 that are going to stay in aqueous solution here, that stay dissolved. If we looked at our solubility rules, we'd see all of those are going to be soluble. And then 1 that's our precipitate right here, that because of the fact it's a chloride, and so if we, let's say silver chloride, let's take a look back at our rules here. So we said for chlorides, according to this, are typically soluble unless they are silver, and this is silver, so therefore it's insoluble, and so that's the reason why it does form a precipitate here, and so why this ends up being an S and precipitates out as opposed to the other guys, which all stay dissolved. So what we want to do is we want to write these out as ions. And so instead of writing out just AgNO3, down here we do the Ag plus in aqueous solution plus the NO3 minus. We've broken this guy up into its two ionic components, into the ions that would actually be in solution, because remember that ionic substances, whenever they're dissolved, don't stay together. The ions actually separate out as they get attracted to the different polar ends of the water molecules. In the same way over here, as we can take NaCl, the Na ion will write out, the chloride ion will write out right here. Now, the AgCl, that silver chloride, remember, is insoluble. It's the precipitate. So we're not going to write that out as ions. We're going to keep that in the same form it was before, because since it doesn't dissolve, it doesn't break up into ions. They stick together. And so we're going to keep it as a compound, because it's not an ionic substance that's dissolved in water, because it's the precipitate, because it's the insoluble substance. Now, NaNO3, on the other hand, is still ionic, is an aqueous solution, and so we're going to write it out in ions. So we say Na plus, and then we're going to write out our nitrate ion over here. And so this formula right here that's written out is the total ionic equation for this reaction, listing every single ion that's involved in that particular reaction. So, I want you to notice something. In this total ionic equation, the one I have still written down here, same equation for the total ionic equation, look at the Na plus, the sodium ions, and the NO3 minus, the nitrate ions. So sodium ion is right over here, right? So it starts off on that side, and on the other side, it's still a sodium. I mean, not a sodium ion, sorry, I'm looking at the wrong one here. So look at the nitrate ion, so look at the nitrate NO3 ion on both sides. It's a nitrate ion on both sides here. It really hasn't changed its position. Let's look at the sodium ions. The sodium ions is Na plus over here. It's still just Na plus over here. Now that's different than the silver. The silver starts off as a separate silver ion but ends up in a compound. The chlorine starts off as a separate ion but ends up in a compound. So the silver ion and the chloride ion have changed. They have reacted. They have participated in this reaction. But really, the nitrate and the sodium haven't changed at all. They really haven't participated in this reaction at all. You know, they started off floating around in water. They ended up floating around in water. They didn't do anything. And so because they didn't participate in the reaction, they're called spectator ions. Because what do you call someone who's at a game but doesn't participate in that game? They're a spectator. And so in the same way, these ions are involved in this reaction, but they don't participate in the reaction, and so they're spectator ions. And so these spectator ions, since they aren't involved in the reaction, it's sometimes helpful to write a simplified version of the total ionic equation that eliminates the spectator ions because really they're not involved. They're not really part of the reaction. And so instead you write out an ionic equation that only includes the elements that are involved in the reaction. And so this type of reaction, simplified down, and doesn't involve the spectator ions, is called a net ionic equation. So using our original total ionic equation, we're going to cross out, we're going to eliminate our NO3s, our nitrates on both sides, because that's a spectator ion. We're going to eliminate our sodium ions on both sides, because that's a spectator ion. And that leaves us just with the silver plus the chloride ion. So you see we have down here, I'm going to rewrite it. So silver plus the chloride ion. And then on the right side, we've eliminated everything but that precipitate, that insoluble silver chloride. And so now, down at the bottom, this right here is our net ionic equation for that original one. Now you see this is a lot simpler than what we had originally here. So we sort of got more complex when we went to the total ionic equation, but then we've simplified it down to the net ionic equation, because this way we're only looking at those particular ions that are involved in the actual chemical reaction, not those that sort of just sit around and around but don't really do anything in the actual reaction.